Hi, today we're going to quickly go over how to derive the energy levels in an hydrogen atom in a fairly rough way using Bohr's ad hoc method. We're not going to use Schrodinger equation and solve it for a 3D potential because the math gets a little ugly, but this method, even though it's somewhat ad hoc and has a lot of approximation, gives us fairly good results. So thinking back, first off, we kind of have an idea that different atoms have different energy levels in their electrons. From the fact that when we excite them into a gas and we heat enough, it emits in these specific discrete lines. And knowing E is equal to h nu, that means specific energy in these transitions. Now, these kind of spectrum, the one for hydrogen is shown here, has been used for a long time, even before Bohr came along in chemistry, to identify different elements in, say, a compound or molecule in different amounts in terms of spectroscopy analysis. But it's more or less a given that, more like a fingerprint, this element has this element has this. The underlying mechanism of why these lines are in specific places was still needing to be explained. This is the lines we get in the visible spectrum for hydrogen. And someone by the name of Balmer stirred this for a very long time. He must have, because he realized that these numbers follow this pattern. He must have been a really good pattern spotter, because I don't know how he got that. But he did. So that was the start of trying to make sense of this. Next step, Rydberg rearranged this in terms of nu to make it look like this. Well, that's sort of interesting. You can see that this 2 here, it looks like we can almost put in any other integer number and get other frequencies of emission, because this here is an integer number. So rewriting that, as long as NA is greater than NB, so we have a positive number, that should give us the frequency for all other transitions. And in fact, it does. If we put NA is equal to 1, we get a bunch of lines in UV, and that's called the Lyman spectrum for the first person. For the first person that kind of observed it. If we put NA equals 3, we're into the IR, and we see that as, we call that the Paschen series. But what this is implying that because E is equal to h nu, it's implying that the energy is somehow directly proportional to an integer square, this n square bit, because we know the photon's only emitted when you transition from one level to another, so that's why you subtract 2 different numbers from one step to the next to another step. You can jump multiple steps, but they all need to be integer numbers because of the quantization. So to try and explain this, Bohr tried and worked it in his model with the electron orbiting the proton. So here's a very rough sketch of Bohr's model. We have a proton on the inside, a single proton for hydrogen, and a single electron zipping around it. Supposedly it's in a stable orbit, so we can actually talk about equilibrium and say that the centripetal force is equal to the electric attraction force, so that's going to be E squared over 4 pi epsilon naught r squared, and Fc is of course mv squared over r, known then V is equal to omega times r, and knowing a bunch of constants, because we know me, it's 9.109 times 10 to the negative 31st. Epsilon naught is another, it's a universal constant. We're going to not write out the unit because they get rather long, but rest assured we're using OSI. Elementary charge, and for the radius we'll use the diameter of the hydrogen atom divided by 2. If we plug all that in, you realize that the omega is in the range of times 10 to the positive 16 radians per second, which gives us a frequency of 2.19 times 10 to the 15 hertz. And if you have something zipping back and forth, a charge that's zipping back and forth at such rate, it's going to likely emit EM waves coming out at the same frequency. And this frequency corresponds to a lambda of 136 nanometers, which is in the UV spectrum. And it'll bleed out these energy quite quickly, and what you get is, as you lose energy, your electron's going to spiral and then fall into the nucleus, which is absolutely absurd because it doesn't happen. We have stable atoms everywhere. So to reconcile this, Bohr came up with this. He suggested that the angular momentum, which is mvr, of the electron is somehow quantized with the constant n times h bar. Of course, n equals 1, 2, 3, so on and so forth. Now, in hindsight, we can understand this as actually somewhat more intuitive way, in that knowing the de Broglie wavelength, we can work this out to be that, and rearranging, we'll get n lambda is equal to pi r. So in a sense, what he ended up saying, maybe without even knowing at the time, is that these matter waves have a certain wavelength, and as the electron goes around the circle, they must form these standing waves so it joins up properly. So if I have, say, 1 wavelength, 2 wavelength, 3 wavelength, and 4 wavelength, to meet up, it has to be perfectly 4 wavelengths. Or we can have similarly 1 wavelength, 2 wavelength, 3 wavelength, like that. So it's actually somewhat intuitively appealing, even though it wasn't so apparent at the time. So with that, we can then work out what kind of energy level is allowed based on this quantization. Again, we still know that E squared over 4 pi epsilon naught r squared is equal to mv squared over r. So then V is E squared over 4 pi epsilon naught mvr, which is then our way of introducing our h bar n. And then the radius can similarly be rearranged to give 4 pi epsilon naught h bar n over E squared m. And with these, we can work out both the kinetic energy and the potential energy. T is equal to 1/2 mv squared. So we have that potential energy, as long as we set the potential to be 0 at r approaching infinity as per normal, we have E squared over 4 pi epsilon naught r with negative. So negative m h bar squared over 4 pi epsilon naught, yada yada yada, 1 over n squared. And then the total energy is, of course, T plus V, which gives us that. And we have the expected result of En is directly proportional to n squared. Sweet. And traditionally, when n equals 1, 2, 3, we call that the K shell, the L shell, the M shell, and so on. So plugging in the numbers, we get negative 13.6 electron volts times 1 over n squared for the nth energy level. So often we like to draw this in a energy diagram. So it's got a well-like thing. At the very top, you have 0 energy at infinity. At the very bottom, you have your 13.6 electron volts. Next level, so this is n equals 1. At n equals 2, you're 3/4 of the way to the top because it's multiplied by 1/4. So you're over here, and that's negative 3.4. Then you go n equals 3, which is 1/9, negative 1.51, then negative 0.85 for n equals 4, and then n equals 5 somewhere up here, and then it just gets denser and denser and denser. So you have an infinite number of energy levels that gets denser and denser as you get closer to 0. And then we can thus kind of understand the Balmer series. The Balmer series is when you go from all these different levels down to level 2. That's why it's 1 over 2 squared. So you can go from 3, you can go from 4, you can go from the 5th state down to the 2nd state. When you have n equals 1, you're dropping all the way down to the 1st level, then when the other series, and so on and so forth. So everything is kind of explained because, just to put things nice and neat, you have this going on. We've swapped it up because it's negative, so it's where you're starting from to where you end up. So we'll call this B and call that A, which is what Rydberg got. And this value, as measured as the escape energy of an electron or an ionizing energy for the hydrogen, it's pretty close. Now there's a couple refining details that that has to be done in order to make it very, very accurate, which involves, first off, because your proton has a finite mass, while the electron zips around, the proton also wobbles a little bit the other way. So we have to take that into account. Electrons inherently have spin and angular momentum, and that allows for multiple states at the same energy roughly, thus giving you the whole 2 electron in the inner shell, 8 electrons, so on and so forth. And ultimately you can use Schrödinger equation to actually look at what the wave function and distribution actually ends up looking like. But we'll leave that for your actual quantum course.